Hello everyone, my name is Richard Jonker and today I'll be presenting our team's work for the BioCreative 8 Challenge SympTEMIST. We are from the University of Aveiro in Portugal and this will summarize our work for this challenge. So to give an overview of the challenge, the challenge focuses on automatic detection and normalization of clinical symptoms. So the first subtrack is related to named entity recognition, where we have to recognize these symptoms. The text is in Spanish. The second subtract is related to normalizing these symptoms to a corpus called the SNOMED-CT corpus. And then the third subtrack is just a general exploratory track where we try to normalize different languages into the same SNOMED-CT corpus. So the work that's presented in this presentation is based mainly off of previous work that our team did earlier this year. So to give a brief overview of our methodology, for the first subtask, which is entity recognition, we focus mainly on token classification, where we use the biotagging scheme. And essentially what the biotagging scheme is that we have three possibilities that we can classify each token as, B being the beginning of an entity, I being inside of an entity, and O being outside of an entity. So using these three different classes, we can easily classify the entities within a given text. In order to do this, we incorporate a model that has three main components. We have a transformer-based model, which in this case is mainly Roberta. We have then an encoder layer, which we use BioSTM for in this case, and then we have a classification head, which is based on mask CRF. We also employ document splitting to be able to split documents that are larger than the context size for the transformer model, and we also provide context for these individual splits. Further, we also employ augmentation and ensembling techniques. So the augmentation that we use is we use two different types of augmentation. The first being random token replacement, whereby we select tokens and then we replace them with a random token from the dictionary. And then we have a specific version of this where we replace these tokens with a specific unknown token. We also experimented with the frequency and the chance of replacing tokens. The ensemble technique that we used was based on the entities predicted. So we have a document and we have models that predicted many different entities, and then we perform a majority voting to determine which of these entities we should be keeping for the final predictions. With regards to subtasks 2 and 3, so these tasks are both related to normalization and follow the similar methodology. So initially we perform a direct matching to see if we have any direct matches from the training data or SNOMED corpus onto the testing data. So if the entity exists in any of these corpuses, we use that definition directly. This was then followed by semantic search using SAPBERT. So essentially SAPBERT will predict or will give an embedding space for the given entity, and then we try to match it with the closest embedding space from either the training data or the SNOMED corpus. And this is done with cosine similarity. And we also set a threshold on this as in some cases it's beneficial to not predict any code, and it's better to leave the code as unknown. With regards to the multilingual task, we perform more or less the same methodology, except we first translate the data from the foreign language into Spanish. And this worked in all the cases except for Portuguese, where we had to go through an intermediate language which was Catalan, as we could not find a direct translation model. So moving now into the results. So these are the results for our first subtask. We submitted 5 models. The first being the ensemble of all the models that we trained. The second being the best performing model on validation, which was trained with unknown augmentation and a 50% chance of altering 20% of the tokens. We then submitted an ensemble of our top 5 models, followed by an ensemble of all the models trained with random augmentation, and finally an ensemble with all the models trained with unknown augmentation. So just a brief overview of the scores. So our best performing model was the one trained with the random augmentation. the ensemble of all the random augmentation. However, most of the ensembles performed relatively similar to each other, and these all perform better than the best performing individual model, which showcases that ensemble techniques do in fact have a significant benefit to the performance of the models, especially on unseen data. We also show that we are above the mean and median of the results in the competition in all these runs. Discussing now our results for subtask 2 and 3. So looking first at subtask 2, the Spanish column. We again submitted 5 different results. So the first model was prioritizing the training text over SNOMED when doing direct matching, as we had overlaps. So in some cases, the codes from the training data and the SNOMED did not match. So we've had to do a priority order. And this was used followed by then a 65% or 0.65 threshold. And comparing between the order of priority, which was between the first and the second run submitted, we do see that the training data priority had a bit of a better performance over prioritizing SNOMED data. We then messed around with the threshold, so we set the threshold to 0 and to 1. So when we set to 0, we accept all cosine similarity pairs, and this slightly reduced the performance of a model, which shows that it is in fact beneficial to not always predict the model in the model. And by setting the score to 1, we essentially only have direct matching. And this shows that while direct matching is relatively strong, we do have a performance gain from performing semantic search. The last model we submitted was just a base model, which was using SAP-BERT base over SAP-BERT large, and this just shows that the performance is not significantly determined by the model size, at least in this case. However, if we do have computational capacity to run the large model, this should be used instead. Again, looking at the comparison to the mean and median, we see that in most cases the models perform significantly above mean and median, except for the model which only had direct matching. However, this was to be expected. And our best performing model was the one with a 0.65 threshold. Looking now at subtask 3, which are the remaining columns with the different languages, and these results are more or less in line with our results from subtask 2. However, it's difficult to compare these with, as we were not provided with the mean or median. However, our preliminary results show that this task is in fact performable, or it is a good idea in fact to perform translation and then performing the same methodology that we used on subtask 2. Finally, just a small conclusion. So this presentation is to summarize our team's presentation at the BioCreative Challenge. In the 3 subtasks we participated in, we saw good results where we performed above the mean and median. We were not given the exact rankings, however we believe we performed relatively competitively. We learned that the ensemble techniques worked well, as well as the data augmentation techniques. With regards to subtask 2, we learned that direct matching is beneficial, and specifically prioritizing the training data over the SNOMED data is important, as we do gain some performance, and this shows us that we are either missing some context within these given examples, or we are probably missing some context, yes. Finally, with regards to the third task, we conclude that it is in fact a viable method to translate the text from a foreign language into Spanish to perform the same subtask as what we did in subtask 2. And that's all. Thank you.